Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about a few additional quote-unquote natural polysaccharides. So, more natural polysaccharides. And in particular, we're going to talk about three polysaccharides. The first one that we're going to talk about is hyaluronic acid. Which is a polysaccharide. And when we talk about hyaluronic acid, we'll talk about two concepts that are related to it. First, we'll talk about polar bonds and the connection between polar bonds within hyaluronic acid and how hydrophilic hyaluronic acid can be. And that's part of basically what makes some of these natural polysaccharides, some of the polar bonds and their connection to hydrophilicity, that basically is what makes many of these natural polysaccharides able to form hydrogels. It's sort of what draws all the water in. So we'll sort of look at some of the structure within hyaluronic acid and draw conclusions, understand the mechanism by which some of this behavior is observed. And then the second thing we'll look at is, particular places in the body where we find hyaluronic acid. And this includes synovial fluid. And we'll talk about the connection between hyaluronic acid's presence in synovial fluid and synovial fluid's viscosity. And just so you can kind of prep yourself, so synovial fluid is the fluid that's in our joints. So most of our joints have sort of two pieces of cartilage. When we move our joints, fingers, wrists, knees, hips, everything, we have two pieces of cartilage that need to slide past one another. They don't just rub directly on one another. There's a layer of fluid in between them, and that fluid that fills up the joint space is synovial fluid. And so we'll talk a little bit about how hyaluronic acid contributes to the viscosity of synovial fluid, and why we might care about that in the context of bioengineering. The next one we'll talk about is chondroitin sulfate, which is another polysaccharide. And when we talk about chondroitin sulfate, we'll talk about how some choices of our biomaterials can actually serve multiple purposes. So chondroitin sulfate can be used in wound dressings or tissue engineering scaffolds. And how it can sort of, in the context of wound dressings and tissue engineering scaffolds, how chondroitin sulfate can basically sort of have a dual purpose in assisting wound healing. Finally, the last natural polysaccharide that we'll talk about is heparin. And you might have seen heparin if you've ever had blood drawn or something like that, or worked in worked in a clinic or something like that. Some of the tubes that you get blood drawn into have a little bit of fluid already in the tube, and for some types of tubes, the fluid already in the tube basically has heparin already dissolved in the fluid. So heparin is a natural polysaccharide. So when we talk about heparin, we'll talk about heparin's connection between, we'll sort of talk about heparin and its anticoagulant effect. So basically, what is it about heparin? What is it about its molecular structure that gives it an anticoagulant effect? And can there be bioengineering uses for heparin beyond just having it in blood tubes, such that when you take a blood sample from a patient, that blood doesn't clot once it gets in the tube? But first, let's talk about hyaluronic acid. So hyaluronic acid which is oftentimes abbreviated HA, in the literature. I mean, HA can stand for a lot of things in bioengineering, and even in particular bioengineering of bones and tissues and cartilage. But anyway, people abbreviate hyaluronic acid HA lots of times. What does its molecular structure look like? Again, you won't be expected to memorize molecular structures in this class, but I'm just going to draw the molecular structure here so we can talk about it and draw conclusions from it. So you'll never be expected to memorize, oh, this is the molecular structure of HA, but rather, if you were given a structure of some polysaccharide or something like that, to sort of draw conclusions about, what are some connections between what's going on at the molecular level and what are some effects that we might observe macroscopically for this material. So hyaluronic acid is basically a repeat of two sugars over and over again. The first sugar looks like this. And the second sugar is linked via this oxygen right here, and a couple of OH groups. And then there's this NH, O, and CH3. And then this basically this one right here connects to an O. That's sort of that is this, and this O is basically the equivalent of this one right here. So I'll sort of draw the boundaries. Basically, where this O right here is sort of equivalent to this O for the next one. So this is what hyaluronic acid. This is what hyaluronic acid looks like. Hyaluronic acid is one particular type of a molecule. So this class of molecules are called glycosaminoglycans. And what are some, like, this is a big long word, right? It's something you would want to use if you wanted to flex a little bit to your non-scientist friends. What are some of the key things here? Well, the amino part of this glycosaminoglycan is basically in reference to the fact that there's an amine, or I guess in this case a modified amine group present on this. And the glycoglycan part are, these words basically are indicating that it's a polysaccharide, right? So the glycoglycan, these sort of indicate that that's made of sugars. So so in a sense, hyaluronic acid in some ways, if I covered up this part, you might look at it and say, oh, this looks pretty similar to, well, what molecule have we seen that looks like this before? A sugar with a COOH group. This side looks a little bit like alginate, right? So this side right here, this side looks like alginate. And if I covered it up and looked at this side, that's a slight rearrangement, not exactly the same, but there's this sort of amine group on these sugars here, and this side, this side here looks a little bit like chitin. It's a bit of a stretch, but so these are sort of, so hyaluronic acid basically has both of them. So it's understandable that in some ways its properties might be similar to these. So what are some key things here? You can create hydrogels from hyaluronic acid by having this carboxylic acid group deprotonate. You can end up with negative charge, right? So hyaluronic acid, the acid part of hyaluronic acid, is in reference to this COOH group right here. So basically this deprotonates, and you end up with negative charge all along the chain. This amine group can't really, it's capped off by this acetyl group right here, so we can't really do anything there, right? This doesn't behave in a base like chitin, or like chitosan does. This is sort of capped off like chitin. But this carboxylic acid group can deprotonate, so we end up with negative charge, and that means that you can create hydrogels via ionically cross-linking hyaluronic acid with divalent cations. In general, glycosaminoglycans, they're oftentimes abbreviated GAGs. And where do you find them? You find them in synovial fluid, which I'll talk about in just a second. But you also find them in cartilage tissues, and in particular in the extracellular matrix. So basically cells within the cartilage manufacture hyaluronic acid, and that basically gives this hyaluronic acid, which I'll talk about its viscous properties in just a second, gives cartilage there's sort of some structure to it. It creates sort of a hydrogel like properties within the tissue to allow for nutrient diffusion, because most cartilage is not permeated by blood vessels, but rather relies on sort of diffusion to bring in nutrients and bring out waste, and it sort of provides this lubricating property. So it's in synovial fluid. It basically it has a lubricating effect. So what's key to this lubricating effect? Well, this lubricating effect is basically how it's related to how well this chain can basically absorb waters. So when you're looking for kind of healthy cartilage-like tissue, you basically want your cartilage tissues to sort of be wet and fully hydrated. So in the extracellular matrix, these glycosaminoglycans basically pull in water and basically make that tissue have the right viscoelastic properties. It basically makes them, smooth and lubricating surfaces. It gives them sufficient sponginess. So in the extracellular matrix, it basically regulates. It pulls in water and creates proper viscoelastic properties. So it draws in water. So take a moment now, pause and ponder, why would a molecule like this draw in water? Well, hopefully you've had a chance to think about it. Why might a molecule like this draw in water? Well, let's just go through this molecule now and highlight all of the bonds that would be polar. So take a moment now, look at this molecular structure, look at it in your notes. Think about which of the bonds would be polar. So which of the bonds in here are polar? Well, basically anytime you have oxygen, which is electronegative, and that oxygen is bound to hydrogen or carbon, which is less electronegative, you're going to end up with a polar bond. So here we have a carbon-oxygen bond that's polar. Here we have a carbon-oxygen bond polar. That one's polar. This one's polar. This one's polar. This one's polar. This one's polar. These ones are polar. This one's polar. 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 I guess this one would be 2. Nitrogen is also electronegative, so nitrogen carbon bonds are going to be polar as well. So that's polar, as well as this double bond that's polar. So if you look at it, there are really it really would have been easier to count the bonds that are non-polar, right? We have just a very small fraction of these bonds that are non-polar. So the key thing here is almost all. And what does that mean? Well, polar bonds, polar things attract other things. So that basically means it attracts water. And that basically means it's hydrophilic. And also soluble. So what does this mean? We have hyaluronic acid. Hyaluronic acid is very hydrophilic, so it pulls in lots of water. It's soluble in water. It attracts lots of water. So in the extracellular matrix, it helps keep that cartilage tissue hydrated. And in synovial fluid, it has this lubricating effect. So imagine I have two pieces of cartilage. For example, like a knee joint right here. And then in the middle of this, I have synovial fluid. And synovial fluid is mostly water, but it has some of these hyaluronic acid chains. It has some of this hyaluronic acid chains in it. So take a moment now, pause and ponder. Do I want synovial fluid? Do I want this synovial fluid to have a high viscosity or a low viscosity? Well, hopefully you've had a chance to pause and ponder. It's actually kind of a trick. It's kind of a trick question. So it depends on what I want to happen. So if I have these two pieces of cartilage, when I'm standing, for example, like this is the bottom of my femur, and this might be the top of my, I guess, my tibia, something like that, right? So these, when I'm just standing here, my weight basically presses my two pieces of cartilage together. So, you know, I might have forces pushing down on this joint. So in compression, I want this to have a high viscosity. So in compression, we want high viscosity. Why might we want high viscosity in compression? Well, if the viscosity is too low, then I'm going to squeeze all of the fluid out of the joint space. So basically, we want high viscosity to avoid collapse of the joint space. Basically, the more viscous that fluid is, the more time it's going to take before my cartilage pieces squish all the way together and start getting cartilage on cartilage contact. So we want high viscosity to prevent leaking too fast. But you might say, hey, wait a second, that's a little counterintuitive, right? This synovial fluid is supposed to be lubricating the cartilage. Don't I want low viscosity if I'm trying to move my pieces of joint, or move my two pieces of cartilage relative to one another, right? I don't want there to be hindrance of the motion of my joints, right? So we want low viscosity to not hinder sliding. So what's the key thing here? Well, actually, this synovial fluid ends up is what's called a non-Newtonian fluid, and in particular, it's a shear thinning fluid. So basically what happens is when the cartilage slides, it basically takes all of these hyaluronic acid chains, straightens them out, and can slide past one another. So when I'm in a shearing motion, it appears to have a low viscosity. But when I'm just standing here, all of the chains sort of coil up and kind of bump into one another. So if I'm just standing here, not really moving, then it ends up with a high viscosity. So actually synovial fluid is a lubricating effect, and in particular, it's shear thinning to get the best of both worlds. In terms of not preventing leaking, but also not hindering sliding. And it's only able to basically serve this function because it is basically very, very long chains of something that is basically has very high polar bonds. This, of course, isn't the only use of hyaluronic acid. Hyaluronic acid appears in a couple other situations, and it certainly has some tissue engineering use outside of synovial fluid. The tricky thing is, sometimes people with arthritis, where they have damaged cartilage, might receive injections of hyaluronic acid into the joint space. And these injections can provide great relief to the patients in that it sort of fills up the joint space with this nice lubricating fluid. The only downside is that our body has, hyaluronic acid is an enzyme that exists in our natural synovial fluid, and basically our body degrades the injected hyaluronic acid over the course of a couple days. So these arthritis patients get an injection, feel great for a couple of days, but eventually that synovial fluid leaks out, or the hyaluronic acid within the joint space is degraded, and they're kind of back to where they started. So, so long term, we're looking for better solutions. Better solutions to treat arthritis than these sort of transient injections of hyaluronic acid. All right, so thus concludes our discussion of hyaluronic acid. Let's now move on to the next molecule that we were going to talk about, which is chondroitin sulfate. So what does chondroitin sulfate look like? Well, it too is a polysaccharide. Again, you don't need to memorize these molecular structures, but I'll just draw it so we can talk about motifs and how impactful they are. So again, there's this carboxylic acid group right here, similar to many of the other polysaccharides that we've seen. OH. It looks like this. There's again, a single oxygen that's binding together two sugars. And here there's something that I'll call OR2. R2 isn't an atom, but rather a group, which I'll define in just a second. And there's OR1 that I'll call here. It's an O, oxygen, and then we basically have an NH, and then that similar CH3O. So in a way, right, this looks pretty similar to hyaluronic acid. Right, this side over here looks pretty much the same. This side over here looks pretty similar in that there's this like NH double bonded oxygen CH3 motif down here. The structure is pretty similar. Only instead of two OH groups here, we have OR1 and OR2. And what's the deal here? So R1 and R2 are either H, and I guess if they were both H, it would look pretty much the same as hyaluronic acid, or they can be a sulfate. They can basically be a sulfate group, hence chondroitin sulfate. So so what would that look like? They can be HSO3. And if you might remember, dust off the high school chemistry, you might remember sulfuric acid. And what is sulfuric acid? So sulfuric acid is H2SO4. And if you sort of look at this, between the O that's here and this HSO3 right here, together it sort of looks like HSO4. Only instead of a second H, the H2, there's basically a bond here. So in a sense, this what would sort of be pure sulfuric acid that you might have experienced in, well, hopefully not directly experienced in high school chemistry, but talked about in high school chemistry. This is sort of like a sulfuric acid, but just bound covalently to this part of the sugar. So sometimes it's an OH group, sometimes it's an HSO3 group, which essentially behaves like sulfuric acid. If you remember, sulfuric acid could exist with H plus and an HSO3 minus, and this could be in equilibrium with two H pluses and an SO4 2 minus. So basically, sulfuric acid was kind of a fungi acid in that it could deprotonate twice. What's the key thing here? Well, we can this guy, this carboxylic acid group, this one can deprotonate and become negatively charged. And these ones can too if they're this HSO3. So these can become minus charged too if they sort of if you kind of imagine like this HSO3 can kick off its hydrogen, and we can essentially have like some SO3 minus as the R1, R2, or both. And I guess just to sort of clarify the extent of this chain, this sequence sort of repeats over and over again. So what's the key thing here? It's basically similar to hyaluronic acid, but could be even more negatively charged. And it turns out that chondroitin sulfate exists naturally in our bodies, and it exists naturally in our bodies as a structural component of cartilage. So this is basically a structural component of cartilage. And what's cool about chondroitin sulfate is it sort of provides that it sort of has a similar effect, like it has a similar effect to hyaluronic acid in that it draws in water, it helps stabilize the cartilage, it helps provide it helps give it a sort of lubricating surface. It by drawing in so much water, it aids in nutrient diffusion to an otherwise avascular space. And one cool thing is you can make wound dressings either partially or completely from chondroitin sulfate. So basically, when applied to wound dressings, it basically has two cool effects. The first cool effect that chondroitin sulfate has is it's basically a hydrogel, and it can basically be a scaffold for cells, and it regulates moisture at the wound site. So basically, it's problematic if wounds dry out too much. Then the tissues can become fragile and crack and get more damaged. So scaffold for cells and regulate moisture. But even beyond that, sort of an exogenous chondroitin sulfate on wound dressing, when it breaks down, it's basically a building block for your body to regenerate its own cartilage tissues. So it's a building block for new tissue. So in a sense, it sort of serves an immediate function in terms of helping provide the right environment for the wound to recover, but it also makes the cells that are attempting to repopulate and reconstruct tissue, be it cartilage or something else, cartilage, skin, lots of other soft tissues. When it breaks down, it provides this building block that is exactly what the cells need to regrow the right type of tissue instead of scar tissue or something like that. So, there's evidence that chondroitin sulfate can sort of aid in these natural healing processes. So, thus concludes our discussion. Well, I guess we already talked about hyaluronic acid. Thus concludes our discussion of chondroitin sulfate. Let's now talk about heparin. So if you talk about heparin, heparin is another polysaccharide. And what does it look like? Well, oxygen. And we have, spoiler alert, a carboxylic acid group right here. Same as the others that we've been talking about. And we get O, and we get here. And yeah, so we have a carbon here bonded to an oxygen, and then an HSO3 right here. And then we have an OH right here. So then we have another ring, oxygen, HSO3, and then we have O, OH, and then we have down here NH, and off of this NH, an HSO3, and then we have So what is the repeat unit? The repeat unit is essentially these two sugars repeating over and over again. So in a way, heparin looks pretty similar to other ones we've seen before, right? There's a carboxylic acid group right here, but this, and this, these are all acids as well. These are all acids as well, which basically means that they can, depending on pH, can be minus charged. And of course this carboxylic acid, like that's also an acid that can be minus charged. So for example, if we compare that, if we compare heparin to hyaluronic acid, hyaluronic acid, had a lot of polar bonds, but only one of them could be charged. Here, this has just as many polar bonds, but in addition to sort of, but here, for hyaluronic acid, we had only one group that can be charged, one charged group per two sugars. Here, we essentially have two charged groups per two sugars, right? So this is basically minus charged and more than HA or alginate, or just about anyone, or pretty much any other natural polysaccharide that we've talked about so far. So what does this mean? This basically means that heparin ends up being hugely negatively charged. And if we go back to hyaluronic acid, well, polar bonds were attracting to water. Something being charged is essentially the most extreme case of being polar. Right, so being charged is like extreme hydrophilic. And we'll talk about this in more detail later on in the class, but basically something being super hydrophilic, we'll talk about the details of exactly why, but the more hydrophilic something is, the basically less, so more hydrophilic basically means the less it supports protein adsorption. And if you're thinking about heparin, we talked about heparin as being an anticoagulant. Protein adsorption is basically the first step in thrombosis, aka clot formation. So what's the key thing here? Basically, if you have a bunch of heparin either floating around in solution or grafted onto a surface, this heparin basically makes the surface super duper duper hydrophilic, and even more hydrophilic than some of these other polysaccharides can be. And basically the extreme level of charge that these polysaccharides give the surface make it so proteins basically can't absorb to the surface, and if proteins can't absorb to the surface, then that surface prevents the blood from being able to form clots. So examples, and so this can be used in solution. For example, heparin blood collection tubes. Or, in solution. This can be used in solution, or grafted to a surface. For example, implant coatings. So some people have basically explored heparinizing stents or other blood contacting biomaterials, basically coating the surfaces in heparin to basically make those implants not give the patient a whole bunch of thromboses if those implants contact blood. Of course, the tricky thing is, your body can basically naturally digest some of this heparin, so the durability of those coatings and their long-term efficacy is still something that people are working on. All right, so thus concludes our discussion of a few more natural polysaccharides and connections between their chemistry, and in particular what groups are present, how charged or polar those groups are, and how they might function in a bioengineering context. So thanks for watching, and good luck with your study of biomaterials.